Welcome to another episode of Short and Sweet Science. In this case, we're going to be talking about motion in one dimension. On the screen, you see a copy of the page from the Cartoon Guides to Physics. So if you've not read this or the textbook, most of what I'm going to say to you is going to seem like gobbledygook, or as the commercial would say, blah, 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 blah. Let's see if we can avoid that. You should have read all of these pages. If you've not read this or the textbook, like I said, life is going to be long and hard for you. If you have read it, you'll realize that this is actually a great book, and you probably should get yourself a copy of this material. It doesn't cost that much. I think it's like 20 bucks for the book. And we're going to go through all this stuff during the next part of this lesson here. Some of this looks like the lesson I gave the other day on the board. That's in the future. And hopefully this will all make a little bit of sense to you. Now, if I've adjusted the computer correctly, you should be seeing on the full screen, instead of just a small part of the screen, a sheet that gives you some of the things we need to look for when we're trying to solve a problem. First part of this is eventually we're going to be looking to fill in this sheet of paper. Let's go through step by step. Problem solving. Step one, what is the question? Then what is the real question? And sometimes the initial question isn't what you think it is. 2, what is given to you for free? Make a list. Step 3, what mathematical representation of nature might apply to this situation? That'd be the math formulas. Step 4, convert combined known relationship from the general form to one that applies to the situation. So if you have to go from inches and feet into meters and kilometers, you do that. Then you find the formula that goes with it, move the letters around. Basic kinematic. Here's the basic list of what we're going to be solving for or looking to find. Time final, time initial, change in time, which is the delta, change in distance, which is distance initial, or not change in, but just the distance initial, distance final, change in distance, velocity final, velocity initial, the average velocity, sometimes is written with a bar over the top. Same thing for the acceleration. Now, in this course, we're always going to be dealing with average acceleration. We're not going to be having change in accelerations, and we're not going to be having a lot of non-constant accelerations. Otherwise, you'll just get a headache, and we're still doing the first part of this motion here, so we have that. The basic kinematic equations, see if we can interpret them. You got speed average or velocity average in this case, because we're in one dimension, therefore there is no direction. It's just the one direction, either plus or minus. So we can call it either one, change in distance over time, or we call it delta t over delta d over t, or v over dt. Velocity average, first velocity, second velocity, third velocity, all the way out to whatever number divided by the number. Usually you have 2, so it just turns out to be velocity final plus velocity initial divided by 2, or if you like formulas, there you go. Velocity final also can be represented as what you started with, plus the acceleration times multiplied by the time you changed it. Distance can also be interpreted as the distance initial, plus how fast you were going for how long you were going, plus how much you changed your velocity multiplied by time squared, multiplied by a half. And there's also one that doesn't even have a t in there. Everything else has t's. This is called the time-independent equation. Your velocity final squared equals velocity initial squared plus 2 times acceleration times distance. If you take this formula, solve it for t, and then put that t back into the formula, you get this guy. So let's see what we have given our givens. Once again, we're back to our little check sheet so you can go through this. I made a few copies of this for those who want to use it initially until they can figure out what they are or are not doing, and then we can get into the problems that we're about to solve. Here's some problems that we're going to attempt to solve here, or we're actually going to do it, and go through them one by one for you. First example, a car goes 30 miles in 30 minutes. What is the average velocity and distance in the SI measurement system? First thing we're going to do is we're going to go back to our sheet and say, what do we know? What do we want to know? It gave us delta t is 30 minutes. It gave us change in distance is 30 miles. Well, this isn't quite useful to us. First of all, we're doing everything in meters per second. So how many kilometers are in 30 miles. So we have D equals 30 miles. Well, it turns out that 1 kilometer, or actually, more importantly, 1.609 kilometers is equal to 1 mile. So we can use this relationship to go 30 miles times 1 mile, 1.609, and then you go to the calculator and you go 30 divided by, or not divided by, but multiplied by 1.609, and this gives us 48.27 kilometers. As far as that goes. Now with that, we can change 48.27 into meters by knowing that 48.27 kilometers, well, we have the relationship of 1 kilometer is equal to 1,000 meters. So multiply it times 1,000. And this gives us 48,270 meters. Now we're going to assume that they gave this to us with at least 2 decimal places. That way we can always start with, so that in 2 decimal places. So this becomes 4.827. Now how many places am I moving the decimal? 1, right? Or kilometers. Not decimals, but 1, 2, 3, 4 times 10 to the 4th meters. Now that we have that, we can go over here and go change in distance becomes 4.827 times 10 to the 4th meters. 30 minutes. Well, once again, we can do 30 minutes, and we all know that there are 60 seconds in 1 minute. So this gets us 30 times 60, which is 1,800 seconds. And then we can figure this out. 1,800 seconds. We can assume from the frame of reference and information I gave before is that if I don't tell you what the starting time is, this is initial. The final time was 1,800 seconds. They didn't tell us what the initial distance is, so we can say 0. We know that change in distance would be then 4.827 times 10 to the 4th meters. We don't tell you what the initial velocity is. We can assume that is 0. Velocity average, we already know from the formulas down here, is change in distance over time. So we go d over t. This becomes 4.827 times 10 to the 4th meters divided by 1,800. I should probably put that in scientific notation too. 1.8123 times 10 to the 3rd. And we go 4.87 or 827. Put this in scientific notation. So 48 divided by, and this gets us 2.682 times 10 to the 1 meters per second, or if you like, 26.82 meters per second. At some points you do have to decide what is the more convenient thing to do it. When it takes you more to write the answer than the answer is written the short way, this is usually pretty good. So we could have called this 48,270, 48,270 meters. As far as that goes, change in velocity. Well, if we go over here to velocity final initial, we can simply say change velocity is final minus initial. Well, we need to know what velocity final is. Well, velocity final can be taken from the average, which is this one here. So velocity final becomes velocity average minus velocity initial times 2. So first we would multiply it by there. So to that, so 2 times the velocity average. So 2 times 26.82 minus 0. And this gives us 53.63. And of course, we had 26.82 meters per second. Velocity final equals meters per second. We could have also figured out what acceleration is using this formula if you like, but that wasn't part of the question because the original part of the question was what is the average velocity and distance in SI measurements? As long as we're here, let's finish it out. A equals velocity final minus velocity initial over time, which means delta V over delta T. We had 53.63 divided by 1800 seconds. So 53.63 divided by 1800 equals 0.0297 times meters per second squared. So this thing is accelerating at approximately 3 centimeters per second, to give you an idea of what this is, because this is less than a meter. 1 centimeter would be right here. And that's as far as that problem can be taken. Now for the next problem, which was the car goes 40 meters in 5 seconds. What are all the values that can be determined from these two values? Well, I filled in a couple here. Here was the 40 meters in the distance. We assumed 0 at the beginning. 5 seconds. We assumed 0 at the beginning, so we've got that one done. So velocity average equals change in distance over change in time. So that gives me 40 meters over 5 seconds equals 8 meters per second. I hope you don't need a calculator for that one. Change in the velocity. Well, I went from, this is the average velocity. What's my velocity final? Well, velocity final is equal to 2 times velocity average minus velocity initial. So that would be 16 meters per second minus 0 equals 16 meters per second. Initial velocity was 0 since we didn't tell you what it was at the beginning. So change in velocity will be velocity final minus velocity initial, which is equal to 16 meters per second minus 0 meters per second, which is equal to 16 meters per second. Acceleration is equal to change in velocity over change in time. Well, we already determined the change in velocity was 16 meters per second times the change in time, which was 5 seconds, which would be 1 over 5 seconds. Let me put an SEC here, and then we go 16 divided by 5, and that gets us 3.2 meters per second times second, which is 3.2 meters per second squared. And if you noticed, I filled in every value that's possible on our little laundry list here, based on what we had down here.